So when we finished on Tuesday, we had this version of a increasing annuity where the payments go up every period arithmetically instead of geometrically. So instead of a percentage increase, we have a flat increase. So we've got a present value formulation and a future value formulation. And I said I would do an example. There are two in the text. And when I read this example, it was very weird to me. So let's work this through. Here's Mary. Mary puts 1,000 at the end of each year. The account she's depositing into earns 9% for 5 years. I am convinced Mary is not listening to her financial advisor, because what she does is she takes the interest out every year and puts it in a different account. The separate account also earns 9%. This is why I think Mary is not being smart here, because if both accounts are earning the same thing, why not just leave them in one bank, not worry about transferring funds? Not my circus, not my monkeys. She's entitled to do however she wants. John also deposits 1,000 a year, but he does it at the beginning of the year. His account earns 10%. Again, for 5 years. He also removes the interest every year, puts it in a different account. But John's separate account only earns 8%. So while Mary is doing something strange, I think John is doing something dumb. Why would you take money out of an account earning 10% and put it into something earning 8%? Unless there are other restrictions on these accounts, like you have a deposit account and a drawing account, you have a principal investment and then a spending account. Lots of businesses and trust accounts operate in this fashion. I would like to know the difference between these two accounts at the end of 5 years. Let X equal Mary's future value, Y equal John's future value. And let's find Y minus X. At least I think John's going to be earning more. Why do I think John's going to be earning more? There are two different reasons here. He's at 10% as opposed to 9%, but also John's money goes in at the beginning of the year and thus has longer to earn interest as well. Not only is it earning interest at a higher rate in the primary account, but it's there longer. Okay. So let's start with what I think is the easier one. What's Mary's future value? Now I'm going to do this as two separate accounts. So when I think of Mary, each year, she's putting $1,000 into this primary account at 9%. But she takes all the interest out. What's in that first account at the end of the 5 years? She does it each year. So 5,000. Okay, that's the easy part. Great. What's Mary's second account look like? All right, wait a minute. That's not intuitively obvious, is it? Let's make a time diagram. If the first account is $1,000 a year, how much interest is earned here? This is a trick question because she hasn't made any deposits before this time, right? Her first $1,000 into the primary account is made at the end of the first year. So her secondary account just gets the interest as it shows up. Wait a second. The interest as it shows up. So what goes into the secondary account and when? Well, there'll be no interest earned in this year. So the secondary account has nothing in it here. Well, how much is earned in interest by this time? $1 year's worth of interest at, so that's $90. But by the time we get to here, how much interest is earned? Remember, I took out this $90, so the balance at this point is, but the balance at this point is 2,000. So at this point in time, there's 180. And now the balance is 3,000. So at this point, the interest is 270. Now the balance is 4,000. So the interest is 360. Do you see the increasing nature of the deposits? Arithmetically, not geometrically. It goes up by 90 every time. So we can think of this as 90 times 1 times 2 times 3 times 4. There's my arithmetic sequence, which makes this account an arithmetically increasing annuity. That's what that IS symbol meant. How many deposits are made? In the secondary account, there are only 4. And the secondary account is earning 9%. So now I can jump back to the formula we had from Tuesday and say, oh, the correct valuation of this account is S 4.09 minus 4 plus 1 over 0.09. So this is where I now need this formula. 1.09 to the fourth minus 1 over 0.09 minus 5 over 0.09. Oh, I forgot to write down the 90. Whoops, bring over the 90 here. Give me a number. Oh, okay, thank you. Oh, hang on a second. Looking back at my formula and realizing there's an S double dot here. I didn't do the double dot, did I? Yeah. It's actually a typo from before. This is my mistake right here. This is correct. This isn't. There should be an n plus 1 here. If this is n plus 1, this should be n plus 1 as well. Because when I go from double dot to no dots, that's what the transition is. And I had to go back and double check the formula. I apologize. That's why we have the formula sheet. So that should be not to the fourth, but to the fifth here. Because otherwise we get a negative number, and that's wrong. I'm not losing money at 9%. 1.09 to the fifth minus 5 divided by 0.09. What do we get for this value? Which means in addition to the 5 grand that's in the other account, she's got 5984.71. By the way, because both accounts are earning 9%, if she just left it all in the first account and done a regular ordinary annuity, she'd have the same value. I don't know why she's moving the money, but she is. Mary's future value is 5984.71. What about John? Well, again, John's primary account has 5 grand in it because he's moving the interest. What does his secondary account look like? So his deposits start at the beginning of the year, which means his interest payments are moved forward. Oh, wait a second. What's his account earning? 10%, not 9%. But that also means he gets money here. So while his first account is the same, his secondary account now has a increasing setup at 100. Now, notice I'm using IS because I'm considering that 100 deposited at the end of the first year, in spite of the fact that his other deposits were made at the beginning of the year. Because we're stripping the interest and moving it, I can think of that as end of year payments. So how many payments get made? At what interest rate? Right, because this is where he goes down. If we want to use the N version instead of the N plus 1 version, we can, but otherwise this is 100 S 6.08 minus 6 over 0.08. So what do we get for this number? Perfect. Which is larger, which means John's future value is bigger than Mary's, and we can compute the difference. difference of $685.20. So even though John is moving to a lower value interest-bearing account, he still ends up earning more because he's moving a little more money, 10 additional dollars each month. Questions? If I work with present value, the same idea still holds, but there's an additional advantage to working in present value. Assuming payments go up as we go forward in time, we can consider what happens if payments go up forever. Like we do with a perpetuity in general, I can do an increasing perpetuities. But then I would really need to take the limit of this thing that we just came up with our formula for here. This is the formula we had from Tuesday. What's going to happen is n goes off to infinity. Advantage, we already did part of this. The 1 over I is a constant. I just pull it out front. The limit of an is a infinity. Double dots. And we know the value for that. Somewhere in the formula sheets that we looked at previously. I know that one. That has a value I know. But then I need to figure out the limit of n v to the n as n goes to infinity. This is much easier than it looks, I promise. Remember that v to the n is 1 plus I to the minus n. So I'll write it with a 1 plus I to the n in the denominator. And from our formula sheets for a perpetuity, the present value of a perpetuity due, that's what the double dots are, is 1 over the discount rate. All right, wait a minute. Why is this limit easy? Why? Exponentials in the bottom, linear in the top. Big O of n over big O of e to the what? No, forget it. The exponential wins. Long as the base is bigger than 1, the exponential wins. So this is 1 over I times, let's see, that's 1 plus I over I minus 0. Wait a minute. 1 plus I over I squared. That's 1 over I squared plus 1 over I. A payout that increases in value arithmetically, maybe it only adds a quarter every year, is still going to be evaluated as a perpetuity in this same vein. But then my limiting value is fairly simple. There's an example in the textbook that alternates years. And I like this example because I think it's interesting in a way we set up. Suppose that my annuity does this. It does some value 2 times in a row. Then it goes up 2 times in a row. Then it goes up 2 times in a row, and so on. Well, if I think of this as year 1, year 2, year 3, year 4, year 5, year 6, then what I can think of this as is an annuity that jumps every 2 years, and I have 2 of them, one for the odd years, one for the even years. And the advantage is that that can now be turned into an increasing annuity. Only my ratio, instead of being V, is V squared. Why is it squared? Unfortunately, no. It's within each one that I use V squared. Instead of the interest rate, I use the interest rate squared because I'm only counting every 2 years. So I think of the one on the left as having a period of 2 years, the one on the right having a period of 2 years. Which means I need to use the effective interest rate for 2 years instead of just 1. So I'll figure out one of these, and then I'll add the other, but since it's offset by a year, I'll add 1 more period's worth of interest to that one. Questions? Everything we've done for increasing works for decreasing too. If I'm doing a decreasing multiple, say your payments go down by some fixed percentage every period, well, then I'm just going to use the geometric one because the geometric formula doesn't care if the geometric part is increasing or decreasing. That's irrelevant. If my payments go down arithmetically, at some point they will hit 0. So all decreasing ones that are arithmetically decreasing are finite. They can't be perpetuities. But it turns out, again, the same development occurs, and I end up with the decreasing present value and a decreasing future value in the same way. I really like the future value version here because it really just takes the present value and moves it forward in time. Every one of these formulas is written in terms of an ordinary annuity. When I looked at John's account, in spite of the fact that John's deposits were made at the beginning, the decreasing part was made at the end. Sorry, the increasing part was made at the end. So I was still doing an ordinary annuity. I can do all of these with annuity due. I get one more period's worth of interest. That changes all of these formulas by multiplying by 1 plus I one more time. That's it. That's all it does. The easiest way to do that is to replace the I in the denominator with D, the discount rate, because D is 1 plus I over I. And you'll see in the formula sheets that that's what happens here. There's our formula for the ordinary decreasing with the I in the bottom. It's the exact same numerator with a D in the bottom for the due version. Now, I must tell you, I don't like using D. I like using I. So I simply remember that as having a 1 plus I in the top. To me, it's just a conversion factor. I just want to talk about the setup before I actually do any of the work here. Jeff bought an increasing perpetuity due with annual payments starting at 5 and increasing by 5 until it reaches 100. Then it stays at 100. So we're going to ramp up the payments and then level off. This is a perpetuity, so it's going to go forever. How much should he pay for it? When I figured out what I wanted to do here, I thought of this differently than the book did the first time. My first reaction is I have a payment that ramps up. It goes from 5 to 100. How long does that take? It goes up by 5 every year. Aha. So it says a perpetuity due. So the first payment is at time 0. And the last payment of 100 is at time 19, 20 total payments. That means from 20 on, it's a level annuity, perpetuity, sorry. So I could actually do this as 2 separate pieces. I could do what is the value today of the increasing part, and then I can figure out what's the value at time 20 of the level part, and then bring that forward to time 0. Or what I could do is I could say, well, really, it's level all the way through. It's at 100. But we're going to subtract off 95, 90, 85, 80, 75, 70, because that will allow what he gets to ramp up if we subtract a decreasing one from a level. That actually is a more useful calculation because the level goes forever, and calculating the level perpetuity is easy. And here's the decreasing part that goes away. That's a more direct calculation because they're both based at time 0, as opposed to the one that ramps up and then the one that's level. This is the one that has to be brought back 20 years. This is the one that ramps up. So these are at 2 different valuation points at first. These are at the same valuation point all the way through. I thought that was an interesting difference. And I was very impressed by this because I hadn't thought of it that way. I'd thought of it this way. But that's a harder calculation. Questions? This is discrete, separated payments all the way through every year, every period, every whatever. We had continuous ideas where we used force of interest instead of a rate, in which case I could think of my payments as being made continuously. If I have a sufficiently small period, like let's say we're getting payments daily or at multiple points throughout the day, it might be more useful, it might be more accurate to use a continuous idea. But if I'm using force of interest, then I'm not going to have a payment that is a fixed value. My payment's actually going to be a function. Instead of a payment, I have a payment function, h of t. What this really is it's a rate of payment. Which makes this a word you may or may not have heard already, which makes this a density function, like probability density functions for continuous random variables. So like a normally distributed variable or a Poisson variable or a binomial variable, this is the same idea. I now have a payment density function. Then, if I want the value over any finite period of time, I'm integrating. The question, am I integrating into the future? Or am I integrating back to today? And all that does is it changes what I multiply by. The present value is going to be the integral over my period of time of however many payments of my payment function times v to the t. Why v? Because that's my present value factor. So if I want to know how much to pay for this payment stream today, this is the value. If I want to know its future value, well, then instead of using v of t, I need to use 1 plus I to the t. Oh, wait a second. That's going to go forward. I need to go from the future back. It's m minus t. Because I need to work from that point forward to time m. So I need to make my integral go from that end, not this end. Again, this is not necessarily a trivial integral. But if we have a continuously increasing function, like a straight line, let's just make it easy. What if h of t is t? Well, then my integral would go from 0 to m t v to the t dt. Wait a second. That's an integration by parts problem. I know how to do that. Which, by the way, then turns into look at that A bar, there's my continuous present value formulation. This is my arithmetically increasing. Instead of dots, I get a bar. Oh, wait a minute. I wrote n. These should be m's. M, I. Same thing for future value. Only it's just minus n instead of minus nv to the n. M. M, I promise I need to be consistent in my variable, where delta is the ln of 1 plus I. That's the same exact formulation we were using before. Again, rarely in the real world do I see the calculus-based format for this, because everybody in the real world decides they're either going to compute interest daily as their lowest period, or they're going to use this for nothing more than approximations, at which point you might as well use the daily version, because I can plug that into Excel and let it rip. The fact that these do have valid limits that give me useful information is useful in the theoretical side of understanding how these sorts of annuity behaviors work. And they allow us to drive fiscal policy in reasonable ways under particular assumptions about the force of interest. Again, this assumed an increasing behavior, and it assumed linear growth. Not always a guarantee. Questions? One of the hardest parts of working with annuities with non-level payments is figuring out interest rates. What rate of return do I need to get to have this payment stream work out with this set of deposits and this set of withdrawals at these times? The financial app in our calculator will only find interest rates for level annuities. Excel will only find interest rates for level annuities. So a lot of the find interest rate problems are restricted to working in level. Annuities with limited numbers of varying payments, a balloon payment or a drop payment, can be done. But really what you're doing is you're deducting that one payment and then finding the level part on the rest. There's a very nice command in Excel to do rates. If you look in the help file under rate, it will show you exactly what the setup is. Questions? If my interest rate varies up and down, then over time, I'll have some investment at the start, I'll have some amount of money at the end. I can work out what the rate was effectively in the middle. If I throw money into an investment at L, and I end up with some amount M in the future, then the effective annual rate, the annual yield rate, is the compound interest rate that takes me from L to M. But if I'm not able to make a loan L as a single value, what if I'm going to repay it instead of at one payment at the end, I'm going to repay it as an annuity? Well, then I know that L is equal to KANI. That's the present value of an ordinary annuity. So here's a question for you. You are the lender in this perspective. You lend me money and I pay it back to you. I'm going to pick a nice, easy number. You lend me $100 and I'm going to pay you, I don't know, $10 a week back, plus some interest in there, right? We'll work out the interest at the end. I'll pay you $10 a week until we paid it off. If there's no interest, I pay you for 10 weeks, right? But you get the money. What do you do with it? If you're an investor, you might say, well, I'm going to put this back in the bank somewhere. I lent out stuff. What did I end up with? If you take my $10 at the end of this first week and you put it in the bank, I don't know what the bank is giving you as an interest rate, and we keep going with that, how much will you have made? So they reinvest the money. They end up with some future value. What's their annual yield rate? So I don't know. What interest rate are you going to charge me for this $100 loan? It's a legitimate question. If you're going to loan me money, I expect you to make me pay interest. What's the interest rate you're going to charge? Do I get your preferred customer rate or am I a high risk customer? You have a number in your head for an interest rate. I'll pull one out of thin air. Let's say you're going to charge me 8%. If you want to make a profit, what do you have to do with the payments you get back? If you only wanted to make zero, let's say you wanted to get exactly 8%. That was our I, but L is ANI, 1 plus I to the N. Wait a minute, I see that. That's the same as SNI. In other words, your reinvestments must happen at least at the same rate for you to not lose money on my investment. Let me think about this for a second. Let's bump the numbers up. I take a 10-year loan at 5% and we pay it back. I'm going to give you 3 options on how to pay back this loan. Option 1 is for you to make 10 level payments. Of some amount. to 10 interest-only payments. And a balloon payment. Oh, I didn't tell you what the amount was. A 10-year loan of. Doesn't help if I don't write of. A 10-year loan amount 10K. And a balloon payment of 10K. Interest-only payments for the first 10 years. And then you owe me all of it. Or one single payment in 10 years. All right. First question. In one, what's my level payment? Level payments of blank. What's that level payment? Formula's right up here. Right up the screen. If the level payment is K, then we had K A N I equals L. So our level payment is L over A N I. So my level payment is 10,000 divided by A 10.05. 10 years, 5%. What is my annual payment here? My present value formulation, 1 minus 1 plus I to the negative n. That's our v to the minus n. Sorry, v to the n over I. What do we get? You have your phone. You have your computer in front of you. I know there's a calculator on there too. Absolutely, I agree with you. What do you got for me?
No, I finished off, so every time you have, no.
I don't mind. 1295.05. Okay. In part two, I'm making interest only payments. What's my interest year one? Yep. So at the end of year one, you have $10,000. You owe me 10,500. You give me 500. The end of year two, how much do you owe me? So each year you owe me $500. And then you also owe me 10K at the end. That's the balloon payment. You're paying interest only, and then one big balloon payment. In three, you just don't pay me anything until the very last minute. That means it's like compound interest the whole time. In three, it's one payment. If I give you $10,000 for 10 years at 5% interest, what's your total payment? Or what's the formula for your total payment?
1.05 to the 10.
Because it's 10 years. And that number is now. If you are the lender, you have to make some decisions. If you take the $500 you get in payment scheme 2 and invest it every month, you'll earn more money, right? If you only got the 500, how much would you end up making? If you did nothing but stick the money under your mattress, you get 500 for 10 years, that's 5 grand. Plus 10,000, you make $15,000. So this is a better idea, isn't it? If you take this money every year and do nothing with it, how much will you get? That's even worse, isn't it? I get 10 payments of $1,295. That's $12,950. Oh, crap. So this is the worst possible thing for me to do, is just take the money, put it in my pocket. This is next worst thing for me to do. And this is actually the best thing if I'm not going to do anything with the money. But if I reinvest as we go along, then I can earn a different value. So I'm lending this money at 5%. My hope is that I could earn more back in the interim than 5%. Maybe I can make an investment at 6%. But even if I make an investment at exactly 5%, then these two options get better. As a matter of fact, if I make the investments at exactly 5%, all three of these will end up being equal to this. Because then it will be like the money they gave me went right into an account earning 5%, which is exactly what this is doing right here, isn't it? It's earning 5% all the way along. If I get 3%, I'll end up with a net lower yield. If I get 6%, I'll end up with a net higher yield. And these might be better. But then it's going to depend on what my reinvestment ability is. And then I can work out the yield for my investment. Yes, ma'am.
Even if you're reinvesting like 2%, you're still gonna make more money than if you do the farm.
Right, yeah, because I'm making more than zero. Yes, I will make more money. What would my yield be? Let's say I reinvested at 3%. So let's do the first one. I'm getting 1295.05 at the end of every year, right? For 10 years. And I'm going to put that into an account earning 3%. So that's the future value of an annuity. And it comes at the end of every year, so it's an ordinary annuity. Okay, 1295.05 times 1.03 to the 10th minus 1 over 0.03. Again, I need a number.
$40,000 to 187. No, it doesn't make sense.
I was gonna say, I'm getting money of almost 1,300 for 10 years. I should be above 10,000. I came up with that number. I come up 14,846.30. $14,846.30. Now, wait a second. This was a loan of $10,000, right? At the end of 10 years, I have this much. What's my yield? The yield is the interest rate, 1 plus I to the 10th, that gives me 14,846.30. I can do that. Divide by 10,000. 1.48463 is 1 plus I to the 10th. So I take a 10th root. And I get 1 plus I is 1.0403077, et cetera, which means I yielded 4.03%. So really, in spite of the fact that I said I'm depositing this at something that's earning 3%, compound interest effectively gives me a yield of 4.03%. Even if I just did the interest payment version, we're only doing 500 a month, right? Sorry, a year. I get 500 a year for 10 years. Let's invest that. 500 S 10.03 500 1.03 to the 10th minus 1 over 0.03. Now this should be a smaller number, because now I'm only looking at a $500 investment, not a $1,300 investment. But remember, I get the 10 grand at the end. I got 94 cents on the end of that. Oh, so my actual future value is 15,731.94. And if I want to know the yield, 1 plus I to the 10th times 10,000. So again, I'll take this and I'll get 1 plus I to the 10th is 1.573194. And I'll take a 10th root of that. 1 plus I is 1.046353, so 4.63% yield. Hey, wait a minute. That's actually a better yield for a smaller investment all the way through. Interesting. So what my effective yield is different than the nominal rate I'm getting charged. My nominal rate in both of these cases was only 3%. But the $10,000 at the end repayment, the balloon payment here, netted me a higher yield in the long run. Another way to say this was you would have had to have been paying more interest or being given more interest to earn the same if you deposited just the interest payments. This is why in a lot of return analyses, a lot of stock market analyses, a lot of market fund analyses, you'll see both a yield rate and an interest rate named because they can be so variable based on repayment term. Now, this is all future value based. You coming up with something different, or you were still calculating? Did I do something wrong? Okay, good. Just want to make sure. There was nothing to do with number 3 because number 3 didn't pay me anything in the interim, so I just got all the money at the end. These are future value calculations. I would like to also have the idea of the present value. So what if I did this time diagram moving back to today? Well, then I generate something called the internal rate of return. Internal, I promise I can spell it, rate of return, IRR. The internal rate of return is the rate at which the loan amount is equal to the present value of the payments. For a loan, the internal rate of return is the nominal rate. It's the rate at which the loan was made. So the $10,000 loan we were making at 5%. The internal rate of return is 5%. But let's think about a different loan. Let's think about what happens for a bond. A $10,000 bond pays interest via a dividend at, I wrote it down, I-12 equals 12% monthly. That means we're paying 0.01 a month. I can reinvest. Oh, I've written that down wrong. This is at 6%. So you get a payment of 6%. That's 0.5% every month, right? 0.05 each month. It's $10,000. What's your payment each month? This is like the separate account that Mary and John set up. You're going to take the interest and do something else with it. The bond is still worth $10,000. What's your interest payment each month? That's if we were getting 6% a month. But that's I-12. So that's 0.06 over 12 times 10,000. So it's not 600 a month. It's only 50 a month. It's 6% a year paid out monthly. So what are you going to do with your interest check? Every month you get a check from this company that says, here's 50 bucks. Let's suppose you can invest that at 12. See, that's what happened. I misread which interest was on which line. How much is this worth in a year, or 2 years, or 3 years? If you cash out the bond then, find yield in 12 months, 24 months, 36 months, assuming the bond is cashed out then. So that means you're going to get the 10 grand and the total of your investments. So in 12 months, your total value is 10,000 plus 50 S12.01 because you're investing at 1% per month. This gives me a value of 10,634.13. What's your actual yield? This has been deposited monthly. So my yield would be like compound interest earned every month. That's why I'm dividing by 12 there. So divide 1.063413 is 1 plus I over 12 to the 12. Take a 12th root. What do you get? If I take a 12th root, I get a much smaller number than that. Which I then have to multiply by 12, subtract the 1, and multiply by 12, my yield is 6.16%. So the bond was paying 6, my investments were paying 12, I balanced this out, ended up with 6.16%. You can do this again for 24 months, and 36 months. There's a general reinvestment idea here. Example 26, page 121, walks through this. And I'm not doing it right now because I've just hit the clock. But that's the end of chapter 2. So that means that the problems for chapter 2 are due in a week. I hope you've been cranking on them because there are a lot of them. I don't want you to be caught off guard. I will see you all on Tuesday. Have a wonderful rest of your day.